Hey folks, welcome to Chapter 1, Lesson 7. We're going to begin with 4 quick review problems that are important for you. So, why don't you try this problem? Find the midpoint M of line segment AB for A, x equals -4, and B, x equals 3. Give it a shot. You can pause it, see if you get it right. All right, so there are 2 approaches to this problem, and you need to know both ways. First approach is to say, find this midpoint. I'm going to take an average of the endpoints. What do I mean by that? I mean -4 plus 3 divided by 2. It's how you find the average of any 2 things. You had 2 test grades, 70 and 90. You add them up, you get 160. Divide by 2, you get 80. Just remember that. To take a midpoint, you can take an average of endpoints. There's another approach you need. You need both. To get the midpoint here, we can take this approach. Starting with the left endpoint, that's this one right here, we could add half the distance between the endpoints, that's half the distance, and that'll take us to the midpoint. All right, so -4, which is the left endpoint, plus 7/2, which is half of AB, will get me to the midpoint. No, it's the same number, -1/2. All right, know both ways. Let's try this in R2. Same questions, but now in R2. Find the midpoint in R2 between C -4, -6, and D 5, -1. Why don't you pause it now and see if you can get this done? All right, let's see how we could do this. 2 approaches. First, easy approach, which would be, well, graph the ordered pairs, see where the midpoint is, drive a line through that, make a right triangle, and then make sure you're getting these, right? We don't want lengths, we want this midpoint of the base and midpoint of the height, because that'll give me this ordered pair, which is the midpoint. Great, so what's my approach? How do I get the midpoint of the base? Just like before, the midpoint of the base is going to be the average x value. The left endpoint plus the right endpoint divided by 2 gives me the midpoint of the base. Likewise, if I want to get the midpoint of the height, the bottom endpoint and the top endpoint divided by 2 is going to give me that midpoint. All right, so we just plug in these numbers, and we get those values. What's another approach we could take here? That second approach. Well, nothing's going to change here. You need to graph the ordered pairs. You need to find the midpoint. Drop the right triangle by going for the midpoint of the base and the midpoint of the height. But how else could we get the midpoint of the base and the height? We could say, left starting point plus half the base will get me the midpoint, and the bottom starting point plus half the height will get me the midpoint. There you go. So it'd be like -4 plus 1/2 of this distance, and -6 plus 1/2 of the total distance. Notice you get exactly the same results, 1/2, comma, -3.5 for the midpoint. You need to know both ways in R1 and both ways in R2. All right, that brings us to the new material. All right, hey folks, we are into Chapter 1, Lesson 7, Transformations in the Plane. This material you won't find in the text, but it'll help you with the material in the text. So let's go through it. A function is a machine that receives input, does something to it, then spits it out as output. What is this that you're looking at right here? This is a washer machine. What does a washer machine take in? It takes in clothes. What does it spit out? Washed clothes. What's the function of the machine? To wash. A function is a machine that receives input, does something to it, and spits it out as output. All right, what do you see next? Airplane, and its brand, it's Hawaiian Airlines. So if you had people in Tucson, where would it take them? To Hawaii. So the input is people in Tucson, and the output is people in Hawaii. Can you think of a function, maybe in your home? Maybe you mentioned a dishwasher. Maybe your toaster, a toaster takes in bread and spits out toast. This is what a function does. All right, more preliminary material that'll help you in this in the text. A vector is a geometric object that has both magnitude and direction. Specifically, we're going to be looking at translation vectors. A translation vector tells an object which way to move and how far to go. So look at the blue dot. Right? It's hovering at the origin. This red translation vector tells the blue dot which way to go, namely northeast, and it tells the blue dot how far to go, namely 5 units in this direction. So if we start with the blue dot here at the origin, and we apply this translation vector 3, 4, here's what happens. The blue dot moves to 3, 4. Remember, we had the airplane, in goes the people in Tucson, out comes the people in Hawaii. A translation vector effectively does that. It sends some object to a new location. So it has 2 pieces of information in it. What direction it's going to send the object. In this case, it'll send the object that way. And how far it'll send the object. It'll send the object not 1 unit, but 5 units. All right, how did I know that? Well, this vector right here is the vector 3, 4. So this is a 3, 4, 5 right triangle. So that distance right there is 5. All right, here, this is all from your text. A transformation is a function, a machine, that maps a figure called a preimage onto a new figure called an image. See this triangle right here? It is a preimage. This right here, this arrow is indicating that we're going to move this triangle over to here. So that's the machine, that's the transformation, that's the function. And this right here is the image. Input, output, preimage, image. And this thing right here will be the function of the transformation in this case. So a transformation can change the position, the size, or shape of an object. This right here is changing the position of an object. I think we understand that. You could have a transformation that changes its size. If I had a shrink ray and I shot it at this triangle, the triangle would become smaller, right? Or I could make it bigger. It's called dilation. That's a transformation. Or even I could have something that distorts a shape. A transformation can be noted using an arrow, such as triangle ABC maps to, and so this arrow means, maps to triangle XYZ, and that's important. Do you see here, if we move this triangle over here, all the points move. So A moves to X, B moves to Y, and C moves to Z. You got to keep the points in order. All right. So we know what a function is. It's a machine that takes an input, spits out output. We know what transformation is. It's a function that takes in a preimage and spits out an image, where the preimage and image are figures, usually geometrical figures like this. All right. If you have a rigid transformation, that's a special kind of transformation, a special kind of function. In a rigid transformation, also called a congruence transformation or isometry, the position of the image may differ from the preimage, but the 2 figures remain congruent. Look over here. This triangle, the preimage, and this triangle, the image, are congruent. The transformation moved the object, but never changed its size. If you have a transformation that moves an object in some way, but doesn't change its size, we've got a rigid transformation. We're going to look at 3 types of rigid transformations in this lesson. Okay, the first type is called a reflection. A reflection or a flip is a transformation over a line called a line of reflection. Blue is mapping to green. Preimage is mapping to image. Input is mapping to output. How does a reflection work? See this thing here? This y-axis, it's a line of reflection. And ABC is going to map to FGH. Here, take a look at this animation. You'll notice what's happening. every point is mapping to every point in the image. So A is mapping to A prime, B to B prime, and C is mapping to C prime. Notice the two shapes are exactly the same size. They're congruent. It's a rigid transformation, no change in the shape or size of the object. And also the distances are the same. Each point in the pre-image and its image are the same distance from the line of reflection. B is 2 units away from the line of reflection. B prime is 2 units away. A is 5 units from the line of reflection. A prime is 5 units from the reflection. All right, it's very important that we name these things in the same order. So if we're going to say A, B, C, then we have to say it's triangle F, G, H, because A maps to F and B to G and so forth. All right, second type of rigid transformation is called a translation or a slide. A translation or a slide is a transformation that moves all points of the original figure the same distance in the same direction. No problem, sliding it over here. This red line right here will be called a translation vector. We looked at translation vector earlier. In this case, it moves this triangle this way by this much distance. Right on. So K is going to map to P, J map to M, and L map to Q. So if we talk about triangle JKL, we have to talk about its image being MPQ. Input, output, pre-image, image. This thing right here is describing a function called a translation, describing a rigid transformation called the translation, whose job is just to move an object a certain distance in a certain direction. Here we go. This is a translation. Can you tell what direction the translation is moving the pre-image to the image? Like what direction it's moving? And can you tell how much? Well, it's clearly moving the image to the right. And then if you look here at A, and you look at A prime, you count 1, 2, 3, 4, 5, 6, 7. It looks like this is a translation to the right by 7 units. All right. What might the translation vector be that achieves that? I would say it's the translation vector 7, 0. So translation 7, 0 takes you 7 to the right and up 0. Okay. A third type of rigid transformation, a rotation or a turn, is the transformation around a fixed point called the center of rotation through a specific angle and in a specific direction. Look over here, blue to green, pre-image, image. Triangle RST is going to map to triangle WXY. What's going to happen? You're going to have a rotation about this center of origin right down here. And the rotation is going to be through this acute angle that's right here. And the rotation is going to be in the direction called clockwise. So what's S mapping to? S is mapping all the way to X. How about R? What's it mapping to? All the way to W. And T to Y. All right. Each point of the original figure and its image are the same distance from the center, right? T maps to Y. So this distance from T to the center of rotation and Y to the center of rotation are going to be congruent. Distances are maintained. Okay, what do we have here? Can you tell me? Yes, it's a rotation. What type of rotation? What direction? So you should give me the angle and the direction. Well, this is a rotation in the counterclockwise direction by an angle of 90 degrees. 90 degrees. So A maps to A prime, B to B prime, and C to C prime. It's a rigid transformation, so the triangles are exactly the same size in each case. All right, let's see if we can identify the type of rigid transformation shown as reflection, translation, or rotation. How about this first one here? Remember, it goes from blue to green. Yeah, that's a rotation about the 0.00 called the origin. And how big is your clockwise rotation? About how large is rotation? Maybe 135 degrees? How about the second one? What do you think? It's a reflection about the y-axis. you can tell that this part is reflected over here. This part is reflected over here. It's a reflection across the y-axis. This last one here is a translation. Blue is moving or sliding to green. Pre-image, image. These red dotted lines represent the translation vector. They're telling you that this object is going to move this way by this much. This particular translation vector, I could tell you the translation vector. If you start with this upper corner blue and you get to upper corner green, how do you get there? You move 3 to the left and then 3 up. So this translation vector would be the translation vector 3, 3. Sorry, -3, 3. That's the translation vector. All right, let's try some more. What do we think 1A is? It's a reflection about the x-axis. How about this guy here? Remember, blue to green. It's a rotation about the origin in the clockwise direction. Looks like about 90 degrees. The last one, it's a translation. And how many units are we moving from blue to green? Just look at the top here and the top here. 1, 2, 3.5. It's a translation to the right by 3.5. What would the translation vector be? It would be the vector 3.5, 0, which sends the object 3.5 to the right and up 0. Great. All right, identify the type of rigid transformation shown as reflection, translation, or rotation. Have you ever played this game where you have this toy on your ankle and you spin it around and you skip over it, called a skip ball? Well, if we were to think about this motion and put it on a two-dimensional figure, it might look like this. And that's one point at which the object is out. And here's another point at which the object is out. Okay, what would you call this type of transformation? It's called a rotation. About what? About her ankle. How about this? What kind of rigid transformation or function is this? It's a translation. Which direction? To the right by approximately how many feet? Maybe 4 or 5 feet. Okay. Let's say this was 4 feet. Let's say this was open 5 feet. It looks like maybe it's open 5 feet. What would the translation vector be? It would be the vector 5, 0, because that will take me 5 to the right and 0 up or down. Translation to the right. How about this guy? Reflection, translation, or rotation? It's a reflection about the midline of the body. Or you could say it's a reflection about the y-axis. All right, when figures are transformed on the chord plane, the exact method in which one figure is transformed onto another can be described functionally. In other words, we can have very specific rules for how to accomplish a reflection, a translation, or a rotation. Let's start with a reflection about the x-axis. Here's the rule. The ordered pair xy maps to the ordered pair x negative y. We write xy maps to x negative y. How about a reflection about the y-axis? xy maps to negative xy. What are we talking about here? Let me show you. Okay, do you see that this is a reflection? It's a reflection of A about the x-axis. So as you'd expect, the ordered pair 2, 4, which is A, maps to 2, negative 4. That seems right. Look over here. The rule for reflection on the x-axis is that xy maps to x negative y. So x should map to x and y to negative y. That's exactly what happened. 2, 4, 2, negative 4. What about a reflection on the y-axis? Show an example right here. This maps A to A prime, maps negative 3, 2 to 3, 2. That seems right. Well, look at this reflection about the y-axis rule. xy maps to negative xy. In other words, y is just y, but x gets negated. Is that what happens here? Negative 3, 2 becomes 3, 2. Yes, this negative 3 gets negated and becomes 3. All right. Consider the triangle ABC that has the coordinates 3, 2, 2, negative 2, and 4, negative 5. what's happening here? What kind of transformation? It's a reflection about the x-axis. It is not a translation. It's not a slide. It's a reflection. You might not be able to see it, but C's down here and C prime's up here. A's down here, A prime's up here. B's here, B prime's up here. So it's not a slide. It's a reflection about the x-axis. You see that? All right, what's the rule for reflection in the x-axis? Well, we just said it's xy maps to x negative y. All right, let's do this thing. What will 3, 2 map to? 3, negative 2. If B is 2, negative 2, what's B prime going to be? 2, 2. If C is 4, negative 5, what's C prime going to be? 4, 5. Let's try another one. Here we have blue mapping to green. Blue is the pre-image, green is the image. And what do you see? What type of transformation is this? Okay, it's again a reflection, this time a reflection about the y-axis. A maps to A prime, B to B prime, and C to C prime. Great, let's try it. What's the rule again for reflection of the y-axis? XY maps to negative XY. Notice when you reflect in the x-axis, it is the x value that gets negated. When you reflect in the y-axis, the x value gets negated. Okay. How about A32? Where's that mapping to? So where's A32? Here's 32. Well, it looks like it's clearly mapping to negative 32. 32 maps to negative 32. Excuse me. How about 2, negative 2? Where's it mapping to? Negative 2, negative 2. How about C? 4, negative 5. We're going to negate the x value, so we get negative 4, negative 5. All right, here's one last one. We have a rectangle ABCD right here, ABCD, and we want to reflect it about the x-axis. Here's the x-axis, so we should get, if this was A, B, C, D, we should get A prime, B prime, C prime, D prime. All right, what's the rule for reflection by the x-axis? XY maps to x negative y. Again, reflection by the x-axis negate y, not x. 1, 1 maps to 1, negative 1. 1, 5 maps to 1, negative 5. 3, 5 maps to 3, negative 5. And 3, 1 maps to 3, negative 1. All right, we had our rules there. Now let's have our rules for translation. A preimage is translated along a translation vector. A vector in component form is written as the vector xy. Notice this looks a lot like an ordered pair xy, but it's got hats on the end. Therefore, this is a vector xy, which describes the vector in terms of its horizontal component x and its vertical component y. All right, if you want to have an object translated along the translation vector AB, here's what you do. You take that point xy and you add the A portion of the translation vector to x and the B portion of the translation vector to y, and that gets you a new vector. XY maps to x plus A, y plus B. Right? How far did XY move? It moved A to the right and B up. So XY lands at x plus A, y plus B. Let's see if we can look at an example of that. This is the translation vector negative 1, 2. So AB, in this case, is negative 1, 2. Well, think about that. If you had a translation vector negative 1, 2, what's it going to do? It's going to send an object to the left 1 and up 2. So if here's your starting point, A, 3, 2, translation vectors should move this guy. The translation vector negative 1, 2 should move this negative 1 to the left and 2 up. So that's where A prime lands at 2, 4. Why does 3, 2 land at 2, 4? According to this rule. Well, if this was the order pair 3, 2, if xy was 3, 2, you'd get 3 plus negative 1, which is 1. And you'd get 2 plus positive 2, which is 4. So that's why you wind up at 2, 4. Okay, how about this translation vector? What's it doing? First of all, what is the translation vector? It's the translation vector 6, 0. And what does that do? That moves any object 6 to the right and 0 up or down. Okay, that seems to be what's happening here. If you track the points, start here at negative 5, 5. 1, 2, 3, 4, 5, 6. Right there shows where the, and it does. See? Rigid transformation, objects stay the same side, just slides this guy over by 6. All right, let's try some. For quadrilateral QRST, find the coordinates of the vertices of the image after translation along the vector 7, 1. Translating along 7, 1 moves the figure 7 to the right and up 1. That's what's happening here. If you look at Q, mapping 7 over and up 1 to get to Q prime. 7, 1 is the translation vector. It is the rule or the machine that sends this object to this location. Okay, in order to do a translation along 7, 1, in order to do a translation along the translation vector 7, 1, or AB, what was the rule for translation along translation vector AB? It was this. XY maps to X plus A and Y plus B. All right, so if I start with Q at negative 8, negative 2, what will that map to? All you have to do is add the X component of the translation vector to this guy, so you get X plus A, and the B component of the translation vector to this guy, you get Y plus B. So negative 8 plus 7 and negative 2 plus 1. Negative 8 plus 7 is negative 1. Negative 2 plus 1 is negative 1. How about negative 9, 5? Here's my starting ordered pair. Got to find out where it's mapping to. Well, this translation vector tells me to move 7 to the right and up 1. So I bet I add 7 to negative 9 and 1 to negative 5. I get negative 2, 4. Negative 4, 7 will map to. Looks like it'll map to 3, negative 6. And negative 4, 2, where will that map to? 3, negative 1. All right, let's try another one. For the triangle MNP with vertices M, N, and P, find the coordinates of the vertices of the image after translation along the vector 2, negative 3. All right, so if we want to have a translation along a vector AB, which here is 2, negative 3, along that translation vector, what's the rule? XY maps to X plus A, Y plus B. All you have to do is add the components of the translation vector to the original ordered pair, and you get the new ordered pair. All right, so 2, 3, add 2, subtract 3, you should get 4, 0. Add 2, add negative 3, you should get 6, 3. And then 1, 8 will map to 3, 5. Notice the names. M matches to M prime, N to N prime, P to P prime. All right, final rules. We have to know our rules for rotations. We'll use a few different rotations. The rotation is a function that moves every point of a pre-image through a specified angle and direction about a fixed point called the center of rotation. And in this lesson, we'll typically use the origin as the center when we perform a rotation. Okay, 90 degrees clockwise rotation. That's XY maps to negative YX. Notice the X and the Y are flipping. This is XY and this is YX with a negation of the Y. 180 degree rotation, XY just maps to negative X, negative Y. 270 degree rotation, XY maps to Y, negative X. Notice again, the XY maps to YX with a negation of the X now. These are the 3 types of rotations at this point you just need to know the rules for. And every one of these makes sense if you think about it. Let's look right here. This is what type of rotation? It is a clockwise or counterclockwise? It is counterclockwise. How many degrees? About this angle. It's a 90 degree rotation counterclockwise. So this formula here, the 90 degree rotation counterclocks, XY maps to negative YX should hold. Let's see if it does. What ordered pair is A at? Looks like it's at 1, 2. 1, 2. So what would 1, 2 map to? Well, first you have to switch x and y. So this is switched. So it'd be 2, 1. And then you'd have to negate the original y value. So it'd be negative 2, 1, right? Let's see if that's what we got. Negative 2, 1. So 2, 1 becomes 1, 2 becomes negative 2, 1. All right. How about this one? Parallelogram FG, HJ is going to be rotated 180 degrees about the origin. That's my center rotation. Which way is this blue guy going? He's going counterclockwise 180 degrees. Counterclockwise 180 degrees. All right, so G will eventually map to G prime. F will eventually map to F prime. J to J prime, and H to H prime, like that. What was the rule for 180 degree rotation? XY maps to negative X, negative Y. Well, that's easy. And it's true. Look over here. F's at what? 2, 1. So according to this rule, 2, 1 would map to what? Negative 2, negative 1. Is that what it maps to? Negative 2, negative 1? Absolutely. G is going to map to negative 7, negative 1. And H is going to map to negative 6, positive 3. Why? Because you have to negate both X and Y. Negating 6, you get negative 6. Negating negative 3, you get 3. Okay, 1, negative 3, where's that going to land? Negative 1, positive 3. Let's try another one here. Consider a triangle XYZ with vertices X, Y, and Z. What are the coordinates of the vertices of the image after rotation 90 degrees counterclockwise about the origin? You got to remember the rule. The rule was a 90 degree counterclockwise rotation. XY maps to negative YX. Please continue to note that the X and the Y's are going to switch to Y's and X's, and the original Y is going to get negated. All right, so negative 4, 2. What do I do? Switch the two numbers, so you get 2, negative 4, and negate the original Y. So it's actually going to be negative 2, negative 4. How about negative 1, 1? Switch them. That'd be 1, negative 1. Make sure you negate the original Y value. So that would be negative 1, negative 1. You try this one. 2, 3. What's that going to map to? Negative 3, 2. All right, folks. Your homework then is Chapter 1, Lesson 7, numbers 1 through 20 all. Of course, there's no even numbers in the back of your textbook, so I've posted an answer key for questions 1 through 20 on the assignment. You should see them when you click on the assignment. You can check your work. Make sure you're DCCS and have a great weekend.